The stars streak past like wildfire, the darkness of space twisting and bending around you as your ship hurtles forward faster than light, faster than physics as we know it should allow. This isn't just science fiction anymore. The dream of warp drive, of crossing unimaginable distances in the blink of an eye, has lived in our collective imagination for decades, from the glowing screens of Star Trek to the cutting-edge equations of theoretical physicists. But here's the question that ignites the minds of scientists and dreamers alike. Could we actually build one, not in some distant, abstract future, but in ours? The idea of bending space-time itself to cheat the universe's speed limit isn't just fantasy. It's rooted in real science, in the mind-bending theories of general relativity that suggest space isn't rigid but more like a fabric, one we might learn to stretch, fold, or even tear. Imagine harnessing that power, crumpling the vast emptiness between stars into something you could cross in days instead of lifetimes. The implications are staggering. Neighboring solar systems within reach, the galaxy suddenly feeling smaller, more intimate. But for all the tantalizing possibilities, the obstacles are just as colossal. The energy required, the materials we'd need, the sheer unknowns of manipulating the very fabric of reality, each one a mountain standing between us and the stars. This isn't just a story about technology. It's about human ambition, about the audacity to look at the impossible and ask, why not? For centuries, we've pushed against the limits of what we thought we could do, sailing beyond the horizon, breaking the sound barrier, stepping onto the moon. A real warp drive would be the next great leap, a testament to our relentless curiosity. And while the challenges are immense, the journey to solving them is just as thrilling as the destination. So let's dive into the science, the speculation, and the sheer wonder of what it would take to turn this dream into reality. Strap in, we're about to bend the rules of the universe. The concept of bending space to travel faster than light didn't start in a lab or a lecture hall. It burst onto the scene in living rooms across the world, thanks to a little show called Star Trek. When the USS Enterprise first jumped to warp speed in 1966, it wasn't just dazzling special effects, it was a radical idea dressed up as entertainment. The ship's warp drive didn't break the speed of light. It sidestepped it entirely, compressing space ahead and expanding it behind like a surfer riding a wave through the cosmos. That visual shorthand, stars stretching into streaks, the hum of the engines became shorthand for the future itself. But here's the twist. While Star Trek made warp drives feel intuitive, real physics is far messier. The show's writers needed a way to bypass Einstein's speed limit to keep stories moving, so they hand-waved the details with terms like dilithium crystals and subspace fields. In reality, there's no cosmic cheat code, just equations that hint at how space-time might be manipulated, with consequences we're barely beginning to grasp. Yet fiction's influence on science can't be overstated. The very term warp drive was popularized by Star Trek, and decades later, physicists like Miguel Alcubierre cited the show as inspiration for his groundbreaking 1994 paper on space-time distortion. That's the strange alchemy of science fiction. It takes wild speculation and plants seeds in the minds of future researchers. But where Star Trek shows warp travel as routine, a tool as reliable as an airplane, real-world proposals come with nightmarish caveats. The Alcubierre drive, for instance, would require exotic matter with negative energy, a substance that may not even exist. Then there's the radiation problem. Particles caught in the warp bubble could build up enough energy to incinerate your destination upon arrival. Suddenly, those smooth, engage moments on the Enterprise's bridge seem like a Hollywood fantasy. But maybe that's the point. Science fiction doesn't just predict the future, it inspires it. The communicators in Star Trek became our cell phones. The tablets on the Enterprise evolved into our iPads. Warp drive remains out of reach, but the dream it represents, that humanity might one day reach the stars fuels real research. From NASA tentative experiments with EM drives to private labs probing quantum physics, the line between fiction and reality keeps blurring. After all, every revolutionary idea was once called impossible until it wasn't. Einstein's theory of relativity didn't just rewrite the rules of physics, it built an unshakable wall around the universe. The speed of light, roughly 300,000 kilometers per second, isn't just a limit, it's a cosmic commandment woven into the fabric of reality itself. According to relativity, as an object approaches light speed, its mass balloons toward infinity, demanding infinite energy to push it faster. The math is brutal. To accelerate even a single atom beyond that boundary would require more energy than exists in the entire observable universe. That's why interstellar travel, as we traditionally imagine it, rockets blasting across the void for decades, hits a dead end before it even begins. Proxima Centauri, the nearest star to our Sun, sits 4.2 light-years away. At the speed of our fastest current probes, reaching it would take over 70,000 years. The dream of exploring the stars starts to feel like a cruel joke, with physics holding all the punchlines. But here's where warp drive theorists step in, armed with a sly realization. Relativity never said space itself has to obey the speed limit. Imagine you're standing on a moving walkway at an airport. You can only walk so fast, but if the walkway suddenly accelerates beneath your feet, you're carried forward far quicker than your legs could manage alone. Warp drives exploit that same loophole. Instead of trying to propel a ship through space faster than light, they propose manipulating space itself, contracting it in front of the vessel and expanding it behind, effectively surfing a wave of warped space-time. The ship never locally exceeds light speed within its bubble, but the space around it moves faster than light would in normal conditions. It's like folding a map, bring two distant points close enough, and the journey between them shrinks from impossible to manageable. This isn't just clever wordplay, it's grounded in real equations. Einstein's field equations, the backbone of general relativity, describe how matter and energy curve space-time. In theory, if you could concentrate enough exotic energy, something with negative mass or pressure, you might twist space-time into the precise shape needed for warp travel. The catch: negative energy isn't just rare. We're not sure it exists outside quantum-scale phenomena like the Casimir effect, where microscopic gaps between plates somehow generate it. Scaling that up to warp drive levels would be like trying to power a city with a single-A battery. And even if we cracked that problem, there's the spine-chilling possibility that a warp bubble could accumulate lethal cosmic radiation or annihilate everything at its destination in a burst of Hawking radiation. Yet these hurdles haven't stopped scientists from probing the edges of possibility. NASA Eagleworks Lab has dabbled in warp field experiments, and institutions worldwide dissect Alcubierre's math for hidden workarounds. Some theorists suggest faster-than-light travel might always remain fantasy, while others argue it's merely an engineering challenge we haven't grown smart enough to solve. After all, the Wright brothers once seemed just as delusional. The deeper truth is this: whether warp drives ever become reality, their pursuit forces us to stretch the boundaries of physics in ways that could unlock other cosmic shortcuts, wormholes, quantum tunneling, dimensions we've yet to perceive. The speed of light may be a wall, but human ingenuity has a habit of building ladders. Miguel Alcubierre didn't set out to revolutionize space travel. He was simply playing with Einstein's equations, searching for hidden possibilities buried in the math. Yet in 1994, the Mexican physicist stumbled onto something extraordinary: a theoretical blueprint for a warp drive that wouldn't shatter relativity's sacred speed limit. His breakthrough came from reframing the problem. Instead of asking how to move a ship faster than light, he asked how space itself could be manipulated to create motion without motion. The result was a concept as elegant as it was bizarre: a warp bubble. Picture a tiny pocket of normal space-time encased within a distortion wave where space contracts violently in front of the bubble and expands rapidly behind it. Inside this protective cocoon, passengers would experience no acceleration forces, no bone-crushing Gs, just the surreal sight of stars ahead compressing into a blue-shifted blur while those behind stretch into red-shifted ghosts. Alcubierre's math showed that this bubble could, in theory, propel a ship at arbitrarily fast speeds 10 times light speed, 100, even 1,000 without ever locally exceeding light speed within the bubble itself. It was a loophole carved straight from general relativity's own rules, exploiting the fact that space-time isn't static but dynamic, capable of stretching and twisting like taffy. The equations suggested that such a bubble might require something called negative energy density, a form of exotic matter that defies everyday physics by possessing negative mass or pressure. While no known substance behaves this way, quantum mechanics hints that negative energy might flicker into existence at microscopic scales, fueling speculation that harnessing it could one day be possible. Yet the paper's implications were as troubling as they were thrilling. Subsequent analysis revealed nightmarish side effects. The warp bubble would trap high-energy particles along its edges, amassing them into a deadly shockwave that would obliterate anything at the destination upon arrival. Worse, some calculations suggested the drive might require more energy than exists in the entire visible universe, or that it could only function with physically impossible configurations of negative energy. Alcubierre himself called it a quirk of the math, never expecting it to spark decades of serious scientific inquiry, but that's exactly what happened. His work became a Rosetta Stone for warp theorists, proving that faster-than-light travel wasn't automatically forbidden by relativity, just imprisoned behind layers of engineering and physics we don't yet understand. What began as a playful thought experiment now fuels real-world research. Scientists pore over Alcubierre's equations searching for workarounds, maybe lower energy requirements, or ways to shield against the lethal radiation. Some propose that advanced civilizations might have already cracked the code, their warp signatures hidden in cosmic anomalies we don't yet recognize. Others argue the drive may forever remain a mathematical mirage, beautiful but unreachable. Yet even if the Alcubierre drive never becomes a reality, its legacy is secure. It transformed warp travel from science fiction trope to legitimate theoretical physics, proving that sometimes the most impossible dreams are just equations waiting to be solved. To understand how an Alcubierre warp bubble might actually work, picture space-time as a vast, stretchy sheet, the kind that billows in the wind. Normally, stars and planets create gentle dips in that sheet with their gravity. But a warp drive doesn't just bend space, it violently warps it, creating a ripple so extreme that it distorts distances themselves. Here's how it happens. Ahead of the ship, space contracts like an accordion being squeezed, pulling distant points closer together. Behind the ship, space expands like a balloon inflating at impossible speeds, pushing the starting point far into the distance and right in the middle. A flat, undisturbed pocket where the ship sits untouched, like a passenger riding the eye of a hurricane. This isn't just about moving the ship, it's about moving the universe around it. Think of a treadmill. If you stand still while the belt rolls beneath your feet, you stay in place relative to the machine, but the ground itself is moving. A warp bubble does something similar, except instead of a rubber belt, it's the fabric of reality doing the shifting. The ship doesn't accelerate in the traditional sense, it's carried forward by the warping space itself, sliding through the cosmos like a marble rolling down a tilting table. This means no crushing G-forces, no time dilation effects, just the eerie sensation of watching stars ahead of you compress into a tunnel of light while those behind stretch into dim red smears. But here's where things get mind-bending. The energy needed to twist space like this isn't just enormous, it's bizarre. The front of the bubble requires negative energy, a hypothetical substance that repels gravity instead of attracting it. Imagine trying to push a car uphill, except the hill is actively helping you by tilting downward as you shove. Meanwhile, the back of the bubble needs positive energy so intense it could rival the output of entire stars. And all of this has to be perfectly balanced, like holding a soap bubble steady in a hurricane. One miscalculation and the bubble could collapse violently, or worse, unleash a shockwave of distorted space-time with unpredictable consequences. Surprisingly, nature might already give us glimpses of how this could function. Black holes warp space so severely that time slows to a crawl near their event horizons. Cosmic inflation in the early universe stretched space faster than light itself. Even quantum foam, the seething, subatomic froth of reality, briefly creates microscopic bubbles of distorted space. These phenomena don't prove warp drives are possible, but they hint that space-time is far more flexible than our everyday experience suggests. The challenge isn't just finding the physics to make it work, it's surviving the side effects. Calculations suggest that particles caught in the warp bubble's edges would be accelerated to lethal energies, potentially vaporizing anything at the destination the moment the drive disengages. Yet for all the hurdles, the sheer elegance of the idea keeps scientists hooked. Recent studies have explored ways to reduce the energy demands, perhaps by shaping the bubble differently or borrowing energy from higher dimensions. Some theories even suggest that advanced civilizations might already be using warp drives, their signatures hidden in the gravitational waves we're just learning to detect. Whether or not Alcubierre's metric ever becomes a working engine, it's reshaped how we think about the cosmos. Space isn't just an empty stage where events unfold. It's an active participant, a dynamic entity we might one day learn to sculpt. And if we ever do, the stars won't just be points of light in the sky. They'll be places we can touch. The numbers hit like a bucket of ice water. When physicists first crunched the equations for a warp bubble capable of moving a modest starship, the energy requirements weren't just high, they were ludicrous. Early calculations suggested you'd need negative energy equivalent to the mass of Jupiter just to distort space enough for a 100-meter-wide bubble. Not Jupiter's worth of fuel or matter, Jupiter's worth of exotic, physics-defying negative energy, a substance we've never observed in meaningful quantities. To grasp how absurd this is, imagine trying to power your car by extracting antimatter from a black hole while balancing the entire state of Texas on your roof. That's the scale of impossibility we're dealing with. This revelation came as a gut punch to warp drive optimists. The Alcubierre metric had offered a tantalizing theoretical loophole, but the practical demands made it feel like discovering a treasure map where X marks a spot halfway across the galaxy. Negative energy isn't like gasoline or uranium. It's not something you can mine or synthesize in a lab. At the quantum level, fleeting particles with negative energy might blink in and out of existence, but capturing enough to warp space would be like trying to build a dam with individual raindrops. Worse still, later studies showed that even if you somehow gathered this impossible fuel, the energy density within the bubble's walls would be so extreme it might collapse into a singularity mid-flight, turning your starship into the universe's shortest-lived black hole. Yet here's where science gets interesting. Impossibility is often just a temporary condition. Researchers soon realized that tweaking the shape of the warp bubble could dramatically lower the energy needs. Instead of a rigid, perfect sphere, what if the bubble were more like a flattened donut? Simulations showed this toroidal design might reduce the requirement from Jupiter's mass to something closer to the mass of Voyager 1, still beyond our reach, but no longer cosmically unreasonable. Other teams explored oscillating warp fields that pulsed like a heartbeat, potentially recycling energy in clever ways. Suddenly, the conversation shifted from "this can't work" to "how close can we get?" The greatest obstacle might not be the energy itself, but how we generate it. Negative energy is theorized to appear in phenomena like the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a slight attractive force due to quantum fluctuations. It's as if the empty space between them somehow owes energy to the universe. Scaling this up to warp drive levels would be like trying to power New York City with a single AA battery, but it proves the underlying physics isn't purely fictional. Some speculative designs propose layering thousands of microscopic Casimir cavities like scales on a fish, each contributing a tiny negative energy boost. Others suggest harnessing dark energy, the mysterious force accelerating the universe's expansion, though we don't yet understand it well enough to plug into an engine. What makes the energy problem so fascinating is how it forces us to reconsider what impossible really means. In 1903, the New York Times declared human flight impossible, 9 weeks before the Wright brothers took off at Kitty Hawk. The atomic bomb was once dismissed as fantasy, as were black holes and gravitational waves. History's full of breakthroughs that leaped over unbreakable barriers once someone found the right angle. That's not to say warp drives are guaranteed, only that energy requirements, no matter how staggering, are engineering challenges waiting for a paradigm shift. Maybe the answer lies in manipulating higher dimensions we can't yet perceive, or hijacking the quantum foam of spacetime itself. For now, the dream survives in laboratories where physicists run warp field interferometer tests, searching for microscopic spacetime distortions. It thrives in revised equations that shave zeros off the energy budget with each new iteration, and it persists in the minds of those who look at Jupiter's impossible mass and ask, what if we don't need to carry that weight? What if we could borrow it from the universe itself? The energy problem isn't a dead end, it's the ultimate brain teaser, one that might take centuries to solve. But then again, the stars aren't going anywhere, we've got time. The universe has a funny way of balancing its books. Energy can neither be created nor destroyed, only transformed. But what if some pages in that cosmic ledger were written in invisible ink? That's the tantalizing, maddening puzzle of negative energy. Unlike the positive energy we're familiar with, the kind that powers stars, muscles, and light bulbs, negative energy would behave in ways that seem to flip physics upside down. Picture gravity not as an attraction but a repulsion, like two magnets pushing apart. Matter wouldn't just weigh less than nothing. It would theoretically create anti-gravity, warping space-time in the opposite direction of normal mass. For warp drives, this is the holy grail, the exotic ingredient needed to compress space ahead of the ship and stretch it behind. But here's the catch: we've never definitively observed negative energy on scales larger than subatomic particles, leading to a fierce debate among physicists about whether it's even possible outside of theory. Dive into quantum mechanics, though, and things get weirdly promising. The Casimir effect, first predicted in 1948, offers a microscopic glimpse of negative energy in action. When two uncharged metal plates are placed nanometers apart in a vacuum, they're mysteriously pulled together. Why? Quantum theory suggests that even empty space isn't truly empty. It's a seething foam of virtual particles flickering in and out of existence. But squeeze that space tight enough, and certain particle wavelengths can't fit between the plates, creating an imbalance. The result, a minuscule region of negative energy density, where the vacuum between the plates somehow has less energy than the surrounding space. It's like pinching a water balloon and watching part of it cave inward. The Casimir effect doesn't generate usable negative energy. It's more of a side effect, but it proves the underlying physics isn't pure fiction. Skeptics, however, warn against extrapolating quantum quirks into warp drive fuel. The Casimir effect produces energy amounts so tiny they're practically useless for spaceflight, comparable to the gravitational pull between two grains of sand. Scaling this up to warp bubble levels would require stacking trillions of these nanoscale interactions perfectly, like building a skyscraper out of individual atoms. Even if we could, there's no guarantee negative energy could be stabilized at macroscopic scales. Some theorists argue it would instantly annihilate upon contact with positive energy, like matter meeting antimatter. Others propose that large concentrations might violate the laws of causality, leading to paradoxes where an effect precedes its cause. These aren't just engineering hurdles, they're fundamental challenges to our understanding of reality. Yet the allure persists. Modified theories of gravity, like those involving hypothetical phantom energy, suggest negative energy might exist naturally in the cosmos, woven into the fabric of dark energy accelerating the universe's expansion. If true, harvesting it could be less about creating negative energy and more about tapping into what's already there. Advanced civilizations, if they exist, might have mastered this, leaving behind cosmic signatures we're only beginning to imagine. For now, labs like CERN and Fermilab probe quantum fields for clues, while tabletop experiments attempt to amplify Casimir-like effects. The path forward isn't clear, but it's a reminder that physics' greatest breakthroughs began as heresies. Negative energy might hover on the edge of impossibility today, but so did black holes until we found them. Harold White's office at NASA Eagleworks Lab probably doesn't look like what you'd imagine for a warp drive pioneer. No glowing consoles or floating holograms, just whiteboards crammed with equations that would make most mortals dizzy. Yet in 2012, this unassuming engineer dropped a bombshell. The energy needed for an Alcubierre warp bubble might not require the mass of Jupiter after all. By reimagining the shape of the warp field itself, White's team slashed those impossible numbers down to something almost believable: their secret geometry. The original Alcubierre model envisioned a static, spherical bubble, a perfect warp cocoon around the ship, but nature rarely deals in perfect shapes. White's breakthrough came from asking, what if the bubble wasn't a sphere but a torus, a donut? That subtle shift in geometry transformed the energy landscape. A toroidal field wouldn't just wrap around the ship, it would ripple outward in a dynamic, oscillating pattern, reducing stress on space-time like a well-tuned suspension system. The math suggested energy requirements could plummet from planetary scales to merely the mass of a small spacecraft, say 700 metric tons, roughly the weight of the Voyager probe. Suddenly, impossible started sounding more like maybe in a few centuries, but White didn't stop there. Subsequent refinements introduced the idea of layering multiple warp fields like nesting Russian dolls made of twisted space-time. Each layer could theoretically amplify the distortion while further lowering energy demands. Imagine crumpling a piece of paper. The tighter and more strategic the folds, the more compact it becomes without losing structural integrity. Similarly, a carefully engineered warp field might achieve massive space-time distortions with only modest energy inputs. Simulations showed that under ideal conditions, you might even harness quantum vacuum fluctuations, tiny bursts of energy from empty space itself, to help sustain the bubble. Skeptics, of course, raised eyebrows. Reducing the energy budget was one thing. Finding negative energy sources remained a showstopper. White's proposals leaned heavily on speculative physics, including hypothetical metamaterials that could mimic negative energy's properties. Yet his work sparked something crucial, a shift in how physicists approached warp theory. Instead of dismissing it as fantasy, they began treating it as an extreme engineering challenge, one that might bend but not break the laws of physics. The implications ripple far beyond paper calculations. If energy requirements truly hover at spacecraft scales, the next question becomes how to generate and control such forces. Some theorists propose tapping into dark energy, the mysterious force accelerating the universe's expansion, while others explore particle accelerators as potential warp field generators. White's team even built rudimentary warp field interferometers, devices designed to detect microscopic space-time distortions. Their early results were inconclusive, but the mere attempt marked a milestone. humanity's first lab experiments aimed at bending the fabric of reality. What makes these reductions so thrilling isn't just the numbers, it's the philosophy they embody. Every revolution in physics starts with someone staring at an impossible equation and whispering, "What if we're looking at this wrong?" White's toroidal warp bubble belongs to that tradition, alongside ideas like quantum tunneling and black hole radiation. None of this guarantees we'll ever build a working warp drive, of course. But it proves that the universe's rulebook might have footnotes we're only beginning to decipher. And sometimes rewriting the future starts with redrawing a shape on a chalkboard. Inside a nondescript lab at NASA Johnson Space Center, a device no larger than a microwave hums quietly, its lasers crisscrossing through a vacuum chamber with precision down to the width of an atom. This unassuming box is the warp field interferometer, a machine built to chase ghosts, specifically the ghost of a spacetime distortion so subtle it would vanish if you blinked. The goal, to detect the faintest whisper of a warp bubble, proof that bending space isn't just theoretical sleight of hand but something we might one day engineer. The principle behind the interferometer is deceptively simple. It splits a laser beam into two paths, one potentially passing through a region where space is minutely warped, the other remaining untouched. If spacetime distorts even slightly, the beams will recombine out of sync, creating an interference pattern like ripples overlapping in a pond. Catching that discrepancy would mean spotting a warp effect in action. But there's a reason this experiment feels like trying to hear a pin drop in a hurricane. The distortions scientists are hunting might be smaller than the width of a proton, buried under vibrations from passing trucks, temperature fluctuations, even the hum of the building's air conditioning. Early results have been ambiguous. In 2013, Harold White's team reported a signal consistent with a microscopic spacetime warp, but the margin of error was razor-thin, and critics argued it could have been noise from mundane sources like magnetic fields or thermal expansion. Replicating the findings has proven elusive, leaving the scientific community divided. Some see it as a tantalizing hint, the first flicker of a flame in a dark room. Others dismiss it as wishful thinking amplified by equipment limitations. The truth we don't know yet, but the mere existence of this experiment cracks open a door. What makes the interferometer so fascinating isn't just what it's looking for, it's how it reframes the problem. Instead of demanding Jupiter-scale energies upfront, the device asks a quieter question. If spacetime can be bent at all, even imperceptibly, how do we spot it? Think of it like the first microscopes, crude by today's standards, but revolutionary in proving that invisible worlds existed. If the interferometer eventually confirms even a nanoscale warp effect, it would validate that the Alcubierre drive isn't mathematically impossible, just fiendishly difficult. Suddenly, the conversation shifts from "can we" to "how do we scale it up?" Skeptics, of course, point out the gulf between detecting a warp and harnessing it. Measuring a single ripple doesn't mean you can build a tsunami. Yet history's full of discoveries that began as lab curiosities, X-rays, radioactivity, even electricity before reshaping civilization. The interferometer's true value might lie in its failures. Each dead end forces physicists to refine their models, strip away assumptions, and confront the hard limits of reality. And if it ever works, that flicker in the data could become the blueprint for a machine that bends the universe to our will. For now, the device keeps running, its lasers tracing impossible hopes across the darkness. Whether it ultimately finds warp signatures or not, it's already achieved something profound, transforming a sci-fi dream into a question physics can actually test. And in science, that's often the first step toward turning fantasy into fact. The quantum realm is a place where the ordinary rules of physics dissolve into a shimmering dance of probabilities, and it might just hold the key to unlocking warp travel. At scales smaller than atoms, empty space isn't empty at all. It's a seething ocean of virtual particles popping in and out of existence so fast they're gone before we can detect them. These fleeting disturbances, known as quantum vacuum fluctuations, aren't just theoretical oddities. They're real enough to exert measurable forces, like in the Casimir effect. More importantly, they hint at something astonishing. The vacuum of space itself might be a vast, untapped reservoir of energy, some of it negative. For warp drive theorists, this is electrifying. The Alcubierre metric's need for negative energy seemed insurmountable until researchers realized the answer might lie in these quantum ripples. Imagine the vacuum as a stormy sea. Normally, the waves cancel each other out over time, leaving no net energy. But if you could somehow siphon the troughs the negative energy dips, you might harvest enough to power a warp bubble. It's like trying to bottle the shadows between flashes of lightning, but the math suggests it's not impossible. Quantum field theory allows for localized regions of negative energy density, provided the overall balance remains positive. The challenge: scaling up these microscopic phenomena to something capable of distorting spacetime on a starship scale. Recent breakthroughs in quantum optics offer glimmers of hope. Experiments with squeezed vacuum states have shown we can manipulate these fluctuations, briefly creating zones where negative energy dominates. It's still a million miles from bending space, but it proves the underlying principle isn't pure fantasy. Some theorists speculate that advanced metamaterials, engineered structures with properties not found in nature, could amplify these effects. Picture a lattice of nanoscale resonators, each tuned to trap and magnify vacuum fluctuations like a symphony of tuning forks catching whispers in the wind. Yet the hurdles are cosmic. Quantum effects are notoriously fragile, collapsing when observed or interacting with larger systems. Maintaining a stable warp bubble would require shielding these delicate quantum states from decoherence, like trying to preserve a snowflake in a furnace. Even if we solved that, there's the question of control. Warp fields aren't static. They'd need dynamic adjustment to prevent collapses or lethal energy surges. Some models suggest that AI-controlled quantum regulators might one day manage this ballet, tweaking the field millions of times per second to keep the bubble intact. The wildest possibility: that nature already uses these mechanisms. Dark energy, the mysterious force accelerating the universe's expansion, behaves eerily like a negative energy field on a cosmic scale. Could advanced civilizations have learned to harness similar phenomena? It's a tantalizing thought that the universe's greatest secrets and our path to the stars might be written in the quantum static between the atoms. For now, labs worldwide are probing deeper, from CERN particle colliders to tabletop quantum experiments. Each discovery inches us closer to answering whether warp drive's fuel has been hiding in the void all along. The universe might already be littered with natural shortcuts, cosmic strings threading through space like invisible wires left over from the Big Bang. These theoretical relics, thinner than an atom but with the mass of entire mountains per inch, could warp space-time around them in ways that make warp bubbles look tame. Imagine a string so dense it bends light into a perfect circle if you pass by at the right angle. Now picture two such strings moving parallel at near light speeds. According to physicist J. Richard Gott in the 1990s, this setup could create a time loop, or more tantalizingly, a warp-like corridor where space folds like a folded napkin, letting you hop from one point to another without crossing the distance between them. Cosmic strings aren't the only natural oddities that might mimic warp effects. Domain walls, vast sheets of exotic energy dividing regions of space with different quantum properties, could theoretically compress space ahead of them as they expand. Then there are wormholes, the famed space-time tunnels, which some models suggest could be stabilized by threading them with negative energy cosmic strings. The common thread: these phenomena arise from topological defects, glitches in the fabric of reality where the universe's underlying fields didn't smooth out properly during its fiery birth. Think of them as cosmic scars, wrinkles frozen into space-time that might be harnessable. The allure of these defects isn't just their warp-like properties, but their plausibility. Unlike the Alcubierre drive's need for engineered negative energy, cosmic strings and domain walls would be naturally occurring. If they exist, we wouldn't have to create them, just find and manipulate them. The catch: no one's ever definitively detected one. Their signatures would be subtle, faint gravitational lensing effects, sudden bursts of gravitational waves, or temperature variations in the cosmic microwave background. Some astronomers argue that certain unexplained cosmic phenomena, like oddly aligned galaxy clusters or anomalous gravitational wave events, could hint at their presence. But until we spot one directly, they remain ghosts in the equations. Even if we found a cosmic string, the engineering challenges would dwarf anything humanity has attempted. Moving a string would require energy on stellar scales. Accidentally brushing against one could slice a planet in half like a wire through cheese, and stabilizing a warp corridor between two strings. That's like trying to balance two spinning knives on your fingertips while riding a unicycle. Yet the mere possibility has fueled serious research. Gravitational wave observatories like LIGO are effectively cosmic defect detectors, their lasers sensitive enough to catch space-time trembles from collisions or vibrations of these hypothetical structures. What makes topological defects so fascinating is how they blur the line between astrophysics and science fiction. They're reminders that the universe might have built in loopholes we're only beginning to imagine. For all our talk of warp drives and negative energy, the cosmos might already have highways etched into its fabric waiting for us to read the map. Until then, we're left scanning the skies for distortions that could rewrite the rules of travel, proof that sometimes the most radical ideas come pre-installed in reality. We just have to learn how to turn the key. Warp drives and wormholes might seem like two sides of the same sci-fi coin, but in the realm of physics, they're radically different beasts, each with their own tantalizing possibilities and deal-breaking challenges. Picture the warp drive as a sleek sports car, bending the road beneath it to race forward, while the wormhole is more like a secret tunnel dug straight through the mountain. Both promise faster than light travel, but the paths they take couldn't be more distinct. Warp drives, as we've seen, cheat relativity's speed limit by contorting space-time around a moving vessel. The ship itself never accelerates beyond light speed locally. It's space that does the heavy lifting. Wormholes, on the other hand, are hypothetical bridges connecting distant points in space-time, like folding a sheet of paper until two dots touch. Step through the right tunnel, and you could cross thousands of light years in moments. The difference: a warp drive is all about motion without moving, while a wormhole is about erasing distance entirely. Plausibility is where things get messy. The Alcubierre warp drive demands exotic matter with negative energy, a substance we've never observed at usable scales. Wormholes have their own showstopper. They'd require the same exotic matter just to stay open long enough to traverse. Einstein's equations allow for wormholes, but they'd snap shut instantly under normal conditions, crushing anything inside like a cosmic bear trap. Stabilizing one would be like propping open a black hole's jaws with toothpicks made of anti-gravity. Yet there's a bizarre twist. Some models suggest quantum effects near a wormhole's throat might generate the needed negative energy naturally, at least momentarily. It's as if the universe offers a glimmer of hope before slamming the door. Where wormholes might have an edge is in avoiding some of warp drive's nastier side effects. An Alcubierre bubble risks shredding its destination with accumulated radiation, while a well-constructed wormhole could in theory provide a cleaner passage. But well-constructed is doing a lot of work here. Wormholes large enough for humans would need the mass energy of entire star systems to form, and their stability hinges on physics we barely understand. Meanwhile, warp drives might be more energy efficient at smaller scales. Think probes before crewed ships. Now for the fun part, could these theories ever work together? Some physicists speculate that a warp bubble colliding with a wormhole might create a stabilized tunnel, like a lightning bolt welding two pieces of metal. Others imagine warp highways, where ships use short bursts of warp drive to reach distant wormhole entrances. The wildest ideas involve combining both with quantum entanglement, creating a network where travel is instantaneous across the galaxy. It's the kind of brainstorming that blurs the line between hard science and speculative fiction, but then again, so was the idea of black holes a century ago. What ties these concepts together is their shared reliance on the universe's flexibility. Whether warping space or punching through it, both methods exploit the same truth. Relativity doesn't forbid faster than light travel, it just makes it astronomically hard. The real takeaway, humanity's dream of the stars isn't limited to one narrow path. Wormholes and warp drives represent two branches of the same quest to outsmart the cosmos. And while neither may ever become reality, the pursuit forces us to unravel space-time's deepest secrets one equation at a time. The Casimir effect might be the smallest hint of negative energy we've ever detected, but its implications ripple outward like a shockwave through the cosmos. Picture this: two uncharged metal plates placed so close together they could fit inside a virus. At this microscopic distance, the empty space between them isn't empty at all. It's a seething quantum froth where particles flicker in and out of existence. Normally, these virtual particles cancel each other out, but squeeze them between plates and suddenly, there aren't enough wavelengths to fit. The result: a faint but measurable force pushing the plates together, as if the universe itself is pressing them into a hug. This eerie attraction is proof that the vacuum of space can have less energy than zero, a fleeting glimpse of the negative energy density warp drives desperately need. Scaling this up from nanoscale curiosity to starship propulsion sounds like trying to power a city with a single candle, but the physics isn't completely dismissive. The key lies in the geometry. Casimir forces are strongest when plates are extremely close, typically nanometers apart. To harness this for warp tech, you'd need to engineer structures with countless microscopic cavities, each tuned to amplify the effect. Imagine a honeycomb of plates, each pair separated by precisely calibrated gaps, their combined negative energy adding up like drops in a bucket. Some theoretical designs propose Casimir batteries, layered metamaterials that stack these cavities like pages in a book, theoretically creating pockets of negative energy dense enough to nudge spacetime itself. But here's where reality throws ice water on the dream. Even if you could manufacture such a structure perfectly, the total negative energy produced would still be ludicrously small. The Casimir force between two plates drops off faster than the speed of light, literally. Move them apart by just a few more nanometers and the effect plummets to near zero. To match the energy demands of an Alcubierre warp bubble, you'd need trillions of these cavities working in flawless harmony, a manufacturing feat beyond anything we can conceive today. Worse, quantum fluctuations are notoriously noisy. Stabilizing them across such a vast array would be like trying to conduct an orchestra where every musician is playing a different song at random volumes. Yet the tantalizing possibility keeps researchers hooked. Recent advances in nanofabrication have let scientists create materials with unnatural optical properties, bending light in ways nature never intended. If we could design analogous structures for quantum vacuum energy, say, metamaterials with tailored Casimir responses, we might one day sculpt negative energy like clay. Some theorists even suggest exploiting dynamic Casimir effects, where moving mirrors at near-light speeds could convert virtual particles into real ones, potentially extracting usable energy from the vacuum itself. It's the kind of wild-eyed idea that straddles the line between genius and madness, but then again, so did the concept of lasers a century ago. The Casimir effect's true value might not be as a direct power source, but as a roadmap. It proves that negative energy isn't purely hypothetical, it's woven into the quantum fabric of reality, waiting for us to learn its language. Every experiment that measures these faint forces is like deciphering a single note in a cosmic symphony, one that could one day crescendo into the hum of a warp engine. Until then, the plates keep whispering their secrets, reminding us that sometimes the universe's most profound answers hide in the spaces between almost nothing. If negative energy is the golden ticket for warp drives, then exotic matter is the mysterious black market where we might find counterfeits, or perhaps something even better. Beyond the fleeting quantum whispers of the Casimir effect, theoretical physics offers a menagerie of bizarre substances that could, in principle, twist space-time to our will. Take cue balls, hypothetical blobs of condensed scalar fields that some cosmologists believe might roam the universe like invisible asteroids. These aren't your typical particles. They're more like droplets of an entirely new phase of matter, stable enough to last for eons. What makes them intriguing for warp tech is their potential to carry enormous energy densities, including forms that might mimic negative mass under the right conditions. Picture a cue ball as a cosmic battery, its internal physics so alien it repels gravity rather than attracting it. Harvest enough of them, and you might not need to manufacture negative energy, you could just mine it from the cosmic wilds. Then there's phantom energy, a hypothetical component of dark energy so extreme it makes the universe's current expansion look leisurely. Phantom energy's defining trait. Its density increases over time, threatening to one day rip apart galaxies, stars, and even space-time itself in a Big Rip scenario. For warp theorists, that terrifying property is oddly attractive. If you could isolate and control phantom energy, its repulsive gravity might serve as the ultimate warp fuel, compressing space ahead of a ship with cosmic-scale pressure. The catch, even if phantom energy exists, wielding it would be like trying to harness a hurricane with a spoon. The energies involved are so vast they'd vaporize any known container, and the side effects could include accidentally accelerating the heat death of the universe. For a slightly less apocalyptic option, consider topological defects like cosmic monopoles, magnetic particles with only one pole instead of the usual two. Predicted by grand unified theories but never observed, these oddities could interact with space-time in ways that generate localized warping effects. Some models suggest threading a warp bubble with monopole filaments might stabilize it, like reinforcing a soap bubble with strands of spider silk. The downside, monopoles are thought to be absurdly rare, perhaps one per observable universe, and might require energy levels comparable to a supernova to produce artificially. The wild card in this deck of exotic matter is dark matter itself. We still don't know what it's made of, but certain variants, like actions or weakly interacting massive particles, could theoretically interact in ways that produce space-time distortions. If dark matter isn't just inert scaffolding but an active participant in gravity's dance, future civilizations might learn to tune it like a cosmic instrument, coaxing out warp-friendly effects. What ties these speculative substances together is their defiance of everyday physics. They're reminders that the universe's catalog of materials isn't limited to what we've found so far, and that the next big breakthrough might come from something we haven't even classified yet. The hunt for exotic matter isn't just about checking off warp drive requirements. It's about rewriting our understanding of reality's building blocks. Until then, these theories linger in the shadowy borderlands of science, too compelling to ignore, too elusive to confirm, and too revolutionary to abandon. The moment a warp bubble forms, it becomes a ticking time bomb, a fragile distortion of space-time fraught with dangers that could tear it apart from within. The first threat comes from what physicists call the horizon problem. Inside the bubble, the ship and its crew would be completely cut off from the outside universe, trapped behind an invisible boundary where no light, no signal, no information can reach them. It's like being sealed inside a high-speed elevator with no buttons or windows, utterly disconnected from the world outside. This isolation creates a terrifying paradox. If the crew can't interact with the external universe, how could they possibly steer or stop the bubble? One miscalculation, and you might overshoot your destination by light years, hurtling endlessly through folded space with no way to alter course. Then there's the quantum instability lurking at the edges of the warp field. Space isn't just empty, it's a seething quantum foam where particles flicker in and out of existence. Under normal circumstances, these fleeting particles cancel each other out. But squeezed against the walls of a warp bubble, they could pile up like waves crashing against a breakwater. Theoretical models suggest this quantum turbulence might destabilize the bubble's structure, triggering a catastrophic collapse. Imagine inflating a balloon to its absolute limit, then sprinkling it with microscopic shards of glass. That's the kind of fragility we're dealing with, a warp bubble balanced on the knife's edge between functioning and imploding. But the most immediate danger isn't structural failure, it's radiation. As the bubble plows through space, it would scoop up interstellar particles, compressing them into an ever-growing wall of high-energy radiation at its leading edge. Calculations show that by the time the bubble decelerates, these trapped particles could be accelerated to energies rivaling cosmic rays, enough to vaporize anything at the destination point in a sterilizing blast. It's the ultimate irony. A technology designed to safely traverse the cosmos might annihilate the very place you're trying to reach. Some theorists liken it to arriving in a new city only to trigger a nuclear explosion the moment you step off the train. Attempts to solve these problems only reveal deeper complications. Shielding against radiation would require deflecting particles without disrupting the warp field's delicate geometry, like trying to filter a sandstorm with a sieve made of smoke. Stabilizing quantum fluctuations might demand active suppression systems operating at scales smaller than atoms, a feat far beyond today's engineering. Even the horizon problem has no clean solution. Breaking the bubble's isolation would risk leaking energy outward, potentially collapsing the warp field entirely. Yet these aren't just dead ends, they're puzzles waiting for the right minds to crack them. Recent simulations suggest that oscillating the bubble's shape could shed excess radiation like a ship shedding barnacles. Others propose embedding the warp field within a secondary quantum vacuum layer, essentially giving the bubble a protective skin. The answers, if they exist, will likely come from fields we've barely explored: quantum gravity, higher dimensional physics, or phenomena we haven't even named yet. Every obstacle forces us to dig deeper into the universe's rulebook, searching for paragraphs we might have missed. And that's how progress works, not by avoiding problems, but by confronting them until they yield. The moment a warp drive tears through the cosmic speed limit, it doesn't just bend space, it shatters time. Einstein's relativity isn't just about speed and distance. It stitches space and time into a single fabric, meaning any distortion in one inevitably warps the other. Push past light speed, even via an Alcubierre bubble, and you risk unraveling causality itself. The fundamental rule that causes must precede effects. Picture this: you hop into a warp-capable ship, zoom to Proxima Centauri, then loop back to Earth faster than light could make the round trip. From Earth's perspective, you might return before you even left. Now imagine you accidentally prevent your own launch, a classic grandfather paradox where your existence becomes contingent on an event you just erased. Warp drives don't just compress space, they twist the timeline into knots. These aren't just hypothetical brain teasers. Closed time-like curves, paths through warped space-time that loop back on themselves, are mathematically possible in general relativity, especially around extreme gravitational fields or, say, the edges of a warp bubble. Physicist Kip Thorne demonstrated that wormholes could function as time machines if their mouths are moved relative to each other. Warp drives threaten to do the same by creating a moving pocket of distorted space-time where the ship's local now becomes out of sync with the universe's. It's like two clocks ticking at different rates, except one clock controls reality itself. The real headache comes when you ask how the universe would resolve these paradoxes. Quantum mechanics offers eerie possibilities, parallel timelines branching at the moment of contradiction, or self-correcting events that somehow ensure consistency. Some theories suggest natural mechanisms like quantum vacuum fluctuations might destabilize warp bubbles before they violate causality, acting as cosmic circuit breakers. Others argue that the sheer energy required to create a causality-breaking warp field would always exceed what's physically available, making time loops a self-preventing prophecy. Yet the most unsettling idea is that these paradoxes might simply be allowed. If multiple valid timelines can coexist, a core tenet of the many worlds interpretation, then warp-driven time travel wouldn't erase history so much as fork it. Arriving in your own past wouldn't rewrite your original timeline. It would spawn a new one where both versions of events uneasily coexist. You wouldn't vanish after stopping your grandfather's marriage. You'd just become a stranded anomaly in an alternate universe where your lineage never began. The implications ripple outward. If warp drives enable even nominal time travel, every FTL civilization becomes a temporal power by default. Strategic jumps could let you outmaneuver enemies by arriving before their fleets mobilize. Historical data could be gathered firsthand or altered. The very concept of now would dissolve into a cacophony of relative perspectives. Some physicists speculate this might explain the Fermi paradox. Advanced civilizations avoid warp travel not because it's impossible, but because the temporal arms race that follows is too catastrophic to risk. Ultimately, causality violations aren't just narrative fodder. They're mathematical inevitabilities lurking in the warp drive's fine print. Whether they're deal-breakers or just engineering challenges depends on how deeply time itself resists manipulation. One thing's certain, if humanity ever unlocks warp technology, we won't just be navigating space. We'll be dancing on the edge of a paradox where every leap forward risks unraveling the past. Navigating inside a warp bubble feels less like piloting a ship and more like being locked in a sensory deprivation chamber while blindfolded, hurtling through the cosmos at speeds that defy physics, yet utterly disconnected from the universe outside. The very distortion that lets you cheat light speed also seals you off completely, creating an isolation so profound it redefines the word alone. No star charts update in real time, no radio signals reach you, not even light from outside can penetrate the twisted space-time surrounding your vessel. You're flying through the galaxy with no windows, no radar, and no way to confirm you haven't already overshot your destination by millennia. This isn't just inconvenient, it's existentially terrifying. Imagine setting off toward Proxima Centauri with perfect calculations, only to realize mid-journey that a rogue planet or wandering black hole had drifted into your path. Normally, such obstacles would trigger evasive maneuvers, but inside a warp bubble, you'd never know until the moment of impact. By then, the collision energy compressed at your bubble's leading edge could rival a supernova, obliterating both the obstacle and your ship in a flash of gamma rays. Some models suggest the warp field itself might violently destabilize if it encounters sufficient mass, reverting to normal space mid-flight and subjecting the ship to forces that would smear its atoms across light years. Even worse than the blindness is the helplessness. Without external reference points or communication, there's no way to adjust course mid-flight. Traditional navigation relies on triangulating stars or receiving updates from beacons, but those methods fail when your warp bubble red shifts incoming light into oblivion. You'd be reduced to dead reckoning on a cosmic scale, launching yourself toward a predicted position where your target should be, with no confirmation until you drop out of warp. The margin for error is astronomical. a 1-degree miscalculation at 4 light-years distance means missing your destination by over 70 billion kilometers. Attempted solutions only underscore the problem's enormity. One proposal suggests embedding quantum-entangled particles in the bubble's walls to sense external obstacles through spooky action at a distance, but maintaining entanglement across warped space-time breaks known physics. Another idea involves pre-programming the warp field to collapse automatically if it encounters resistance, like an airbag inflating before a crash. Yet this demands near-perfect knowledge of your route's mass distribution centuries in advance, something no star maps could guarantee. The brutal truth is that until we discover some workaround, warp travel may remain a suicide gamble, a leap into the void where control is an illusion. Perhaps the cruelest irony is that this isolation violates the very purpose of interstellar travel. We seek the stars to connect, to explore, to reach beyond our cradle, but warp bubbles, as currently conceived, force us into a paradoxical exile. You might cross the galaxy, yet experience none of it until the moment you stop. The view from a warp ship's window would be a frozen snapshot of the space you left behind, like staring at a photograph while racing through a hurricane. Future warp engineers won't just need mastery over space-time. They'll need to reinvent what navigation even means when the universe itself becomes unknowable during transit. Even if we cracked the physics of warp bubbles tomorrow, the economic hurdles would dwarf anything humanity has ever attempted. Take those microscopic Casimir effects, the faint whispers of negative energy between nanoscale plates. Scaling them up enough to distort space-time by just 1% might require manufacturing precision beyond today's capabilities, with energy inputs rivaling small nations. The raw materials alone, perfectly polished plates of exotic metals, stacked in arrays spanning kilometers, could cost trillions. Now imagine scaling that to a ship-sized warp field, and you're staring at numbers so vast they lose meaning. For perspective, consider the International Thermonuclear Experimental Reactor ITER, currently the most ambitious energy project on Earth. Designed to harness fusion power, its estimated $50 billion price tag pales next to the infrastructure needed for warp experiments. A functioning warp drive prototype, even at microscopic scales, would likely demand energy grids surpassing global output just to sustain distortions for milliseconds. Quantum-level manufacturing tolerances, where a single atom out of place collapses the effect. Exotic materials mined from space or synthesized in orbital labs far beyond Earth's industrial reach. Economists have tried quantifying this. One study modeled a minimal Alcubierre bubble capable of moving a single atom, estimating costs comparable to building 100 Large Hadron Colliders, roughly $500 quadrillion. That's 30 times global GDP spent to nudge a particle faster than light. Scale it to a crewed ship, and the numbers explode past intelligibility, approaching the energy equivalent of annihilating Jupiter's mass into pure fuel. Yet history suggests even these sums might not be insurmountable, just deferred. The Apollo program consumed over 4% of the U.S. federal budget at its peak, unthinkable for a modern mission. Fusion, renewables, and asteroid mining could one day slash energy and material costs. The real bottleneck isn't wealth but time. Warp research operates on generational scales, demanding investments no single government or corporation could justify without guaranteed returns. The sobering truth: warp drives may only become viable when economics catches up to ambition. When space-based industry flips the equation from impossibly expensive to expensive but inevitable. Until then, the price tag remains the universe's way of saying, not yet. Stepping inside a warp bubble might feel like boarding a roller coaster designed by the laws of relativity, one where the safety harnesses are theoretical and the G-forces could turn your bones to dust. Even if we solved every engineering puzzle, the human body wasn't built for space-time gymnastics. The moment the bubble engages, tidal forces, subtle differences in gravity's pull across your body, could stretch you like taffy. Near the edges of the warp field, gravity might spike to crushing levels while the center remains eerily weightless. A single misstep could mean drifting into a zone where your feet experience a force 10 times Earth's gravity while your head floats free, ripping tendons and rupturing capillaries in seconds. It's the ultimate irony. A technology meant to bridge worlds might reduce its passengers to gruesome physics experiments, but tidal forces are just the opening act. Time dilation, that notorious side effect of high-speed travel, gets even weirder inside a warp bubble. Normally, astronauts on the International Space Station age a fraction of a second slower than Earth-bound humans due to their velocity. A warp drive's distortions could amplify this effect exponentially. Depending on the bubble's shape, you might experience hours inside while decades pass outside, or worse, arrive before you left, tangled in causality loops. Imagine waving goodbye to Earth only to return and find your great-grandchildren older than you. The psychological toll of such dislocation is uncharted territory. Would relationships, careers, or even societal structures survive if warp travelers became unmoored from linear time? Then there's the sensory deprivation. A warp bubble's isolation isn't just technological, it's biological. Cut off from external light, sound, and gravitational cues, the human brain might rebel. Spatial disorientation could trigger violent nausea or hallucinations, like being trapped in an endless freefall. Early experiments with sensory deprivation tanks show how quickly the mind unravels without input. Now magnify that to months or years of void. Some theorists suggest induced hibernation or AI-mediated virtual environments as stopgaps, but these are band-aids on a bullet wound. Evolution never prepared us to exist outside spacetime's rhythms. The solutions, if they exist, might demand redesigning not just ships but ourselves. Genetic tweaks could harden cells against tidal stresses, while neural implants might stabilize perception in a timeless void. Alternatively, we might abandon biological crews entirely, entrusting warp travel to uploaded minds or AI proxies unshackled by flesh. Either way, the dream of humans soaring between stars rests on a gruesome truth. Surviving warp speed isn't just about bending the universe. It's about bending what it means to be human. The moment humanity unlocks warp technology, every treaty, border, and military doctrine becomes obsolete overnight, not just on Earth but across the cosmos. Picture a world where any nation with a warp drive can reach Mars in minutes, mine asteroids before breakfast, or park a warship in orbit over an enemy capital without warning. The balance of power wouldn't just shift, it would shatter, leaving behind a geopolitical free-for-all where traditional notions of territory and sovereignty evaporate. Suddenly, the high ground isn't a mountain or an aircraft carrier. It's the ability to project force anywhere in the solar system before your rivals even finish their coffee. Space law, currently a patchwork of vague UN resolutions and gentlemen's agreements, would face existential stress. The Outer Space Treaty of 1967 bans weapons of mass destruction in orbit, but says nothing about warp-capable kinetic missiles rocks accelerated to relativistic speeds by a drive that bypasses Newtonian physics. Would a warp strike count as an act of war if the attacking vessel never technically crossed sovereign airspace? Legal scholars might argue for decades while militaries quietly deploy warp probes as destabilizing first-strike tools. Meanwhile, mineral-rich asteroids worth trillions become contested prizes, with corporations and nations racing to claim them under conflicting interpretations of peaceful use. The first interplanetary gold rush could ignite conflicts where the battlefields span millions of kilometers and the combatants are light seconds apart. Military strategy would mutate beyond recognition. Traditional deterrence relies on knowing where threats are: nuclear silos, submarine patrol routes, air bases. But a warp-capable adversary could keep their entire arsenal hidden in deep space, emerging only to strike before vanishing again. Early warning systems designed to track Eichbaum would be useless against ships that bypass orbital mechanics entirely. Some theorists predict a return to medieval castle doctrine, fortifying planets with warp detection grids and point defense lasers while maintaining quick reaction fleets in hidden locations. Others warn of doomsday scenarios where rogue states or terrorists acquire warp tech, rendering all borders porous. The ultimate nightmare, a warp-driven asteroid redirected into Earth at fractional light speed, wiping out cities with the energy of 100 tsunamis. A planet killer requiring no nukes, just a ship and a rock. Yet the most profound changes might be societal. Warp capability wouldn't just redistribute power, it would redefine what power means. Nations lacking terrestrial resources could leapfrog superpowers by exploiting off-world riches first. Isolated regions might become interstellar hubs overnight based on their orbital mechanics. And what happens when colonies on Mars or Titan, suddenly just hours away from Earth, demand independence? History suggests that whenever travel times shrink from sailing ships to jet aircraft, rebellions follow. The first warp-reliant separatist movement could ignite with Earth unable to project force fast enough to quell it. Amid this chaos, one truth emerges: no existing institution is equipped to regulate warp technology. The United Nations, designed for a pre-warp world, would need radical overhaul to prevent cosmic anarchy. Some futurists propose a warp non-proliferation treaty, but enforcing it would require policing the solar system, an impossible task when any hidden warp ship could outmaneuver traditional fleets. Others imagine a decentralized blockchain approach where warp-capable vessels are algorithmically tracked via quantum-entangled beacons, but these are stopgaps. The real solution might be as radical as warp tech itself, a new social contract where humanity accepts that the old rules no longer apply, and the only viable path is cooperation at species scale. Anything less risks turning the stars into a battleground where the victors inherit ashes. Every warp bubble that twists space-time leaves behind a faint but unmistakable signature, like ripples spreading across a pond long after the stone has sunk. Now imagine millions of ships crisscrossing the galaxy, each distorting the cosmic fabric in their wake. What happens to space itself when we churn it like this? The environmental stakes might be higher than we've dared to consider. Unlike carbon emissions or plastic waste, space-time pollution wouldn't just endanger ecosystems, it could unravel the fundamental geometry of reality. The first red flag comes from quantum field theory. Empty space isn't truly empty. It's a seething quantum foam where virtual particles constantly flicker in and out of existence. Warp fields could destabilize this delicate balance, amplifying quantum fluctuations until they erupt into macroscopic effects. Picture dropping a pebble into a still pond harmless on its own. But drop 1,000 pebbles per second, and soon the water's surface becomes an unrecognizable chaos. Similarly, frequent warp travel might churn the quantum vacuum into unpredictable states, potentially spawning rogue energy surges or even microscopic black holes at busy interstellar intersections. Then there's the cumulative strain on space-time's elasticity. General relativity treats the cosmos like a stretchy fabric, but even fabric wears thin when pulled too often. Persistent warp activity could theoretically create fatigued regions where space loses its ability to snap back smoothly, leading to gravitational anomalies or localized time distortions. Astronomers might one day detect these scars, patches of space where light bends oddly without visible mass, or where clocks run inexplicably fast or slow. The worst-case scenario, a heavily trafficked warp corridor could degrade into a space-time dead zone, where the natural curvature becomes so warped that nothing can pass through without being shredded. But the most insidious threat might be cosmological. dark energy, the mysterious force accelerating the universe's expansion, seems finely balanced against gravity's pull. If warp drives inadvertently inject energy into space-time's structure or siphon it away, could we accidentally alter that balance? Modest estimates suggest it would take astronomical numbers of warp flights to make a detectable difference, but the risk isn't zero. Tweak the universe's expansion rate too much, and distant galaxies could slip beyond our cosmic horizon forever, their light never reaching us again. It's the ultimate environmental catastrophe, not just polluting our neighborhood but fracturing the observable universe itself. Proposed safeguards range from poetic to paranoid. Some suggest implementing warp lanes, designated routes where distortions are carefully managed, like interstellar highways with enforced speed limits. Others advocate for a leave-no-trace ethic where ships are required to smooth out their warp wakes post-transit, perhaps by emitting counteracting energy pulses. The most extreme proposals involve moratoriums on warp travel near sensitive regions, black holes, neutron stars, or ancient cosmic structures, where additional stress might trigger chain reactions we can't predict. Yet enforcing any of this presumes a level of universal governance that doesn't exist. Earth's history shows how easily environmental agreements crumble when profits or survival are at stake. Would a mining conglomerate reroute its fleet to protect space-time's integrity if it meant losing a competitive edge? Could we even monitor violations when the very act of policing might require warp-capable probes that contribute to the problem? The dilemma mirrors our current climate crisis, but with higher stakes and fewer second chances. Perhaps the sobering truth is that every technology carries hidden costs, and warp drives, for all their promise, might demand a price we're not equipped to pay. Or perhaps we'll discover that space-time is more resilient than we fear, absorbing our distortions like an ocean absorbs raindrops. Until we know for certain, each theoretical warp signature etched across the cosmos serves as a reminder. Some frontiers shouldn't be crossed without first understanding what we might leave behind. Warp drives may dominate the conversation around faster-than-light travel, but they're far from the only game in town. Enter the Krasnikov tube, a bizarre cosmic loophole that turns interstellar travel into something resembling a subway ride. Proposed by Russian physicist Sergei Krasnikov in the 1990s, this theoretical structure is less about bending space and more about laying down tracks. Imagine a tunnel bored through space-time where the return trip takes almost no time regardless of distance. Here's the twist: while warp drives compress space in front of a moving ship, Krasnikov tubes rely on pre-established routes where space-time is pre-warped in both directions. It's the difference between building a highway and magically teleporting, except the highway itself is made of twisted physics. What makes Krasnikov tubes so intriguing is their potential to sidestep some of warp drive's nastier paradoxes. Since the tube's distortion is fixed in place rather than moving with a ship, it might avoid the causality violations that plague Alcubierre bubbles. But the trade-offs are staggering. Constructing one would require manipulating space-time along the entire route in advance, a process requiring energy outputs that could dwarf entire star systems. And unlike warp drives, which theoretically allow for flexible travel, Krasnikov tubes would only connect two predetermined points. Forget exploring new worlds, you'd be stuck riding a cosmic monorail with no exits. Then there's the wormhole network, science fiction's favorite shortcut. Where warp drives and Krasnikov tubes warp space, wormholes punch clean through it. Picture the universe as a sheet of paper. Folding it brings distant points together, warp drive, while poking holes connects them instantly, wormhole. Theoretically, a stable wormhole network could make the galaxy navigable in real time, with transit points functioning like interstellar subway stations. But there's a catch Einstein couldn't solve. Wormholes demand exotic matter to stay open, and not just in small quantities. Keeping a traversable wormhole from collapsing might require negative energy equivalent to the mass of Neptune, concentrated in a structure no wider than a grapefruit. Even if we found a way to gather that much exotic material, the gravitational tidal forces near the throat could shred anything attempting passage into quantum confetti. Comparing these technologies reveals a fascinating pattern. Each FTL method exchanges one impossibility for another. Warp drives offer flexibility but drown in energy requirements and paradoxes. Krasnikov tubes minimize causality issues but sacrifice adaptability. Wormholes enable instant travel but demand preposterous amounts of exotic matter. It's as if the universe is playing a cruel game of pick your poison, offering tantalizing speed while hiding razor blades in every gift. Yet the most radical alternatives might lie beyond conventional physics. Quantum entanglement networks, for instance, propose using spooky action at a distance to transmit information faster than light, though whether this could scale to physical travel remains hotly debated. Dark energy thrusters, another fringe idea, suggest hijacking the universe's expansion mechanism to propel ships. Then there's the truly speculative, higher-dimensional shortcuts where spacecraft exit our three-dimensional space entirely, taking unseen detours through compactified dimensions predicted by string theory. These concepts make warp drives look almost mundane by comparison. The irony, all these ideas, no matter how outlandish, share one sobering limitation: they're solutions searching for problems we can't yet solve. Like medieval cartographers drawing sea monsters beyond the map's edge, we're inventing interstellar vehicles while still struggling to understand the ocean of space-time itself. What unites warp drives, Krasnikov tubes, and wormholes isn't just their defiance of light speed, it's their role as mirrors reflecting our deepest cosmic ambitions. They remind us that the universe's rulebook might have pages we haven't found yet, and that the true engine of discovery isn't just technology, but imagination armored with mathematics. NASA and DARPA aren't content with dreaming about warp drives, they're actively hunting for the physics breakthroughs that might turn them from equations into engines. Behind closed doors and in unclassified white papers, teams of physicists and engineers are dissecting space-time itself, searching for cracks in reality where the rules might bend just enough to let us slip through. This isn't just blue sky theorizing, it's a systematic assault on the known limits of propulsion, backed by funding, computational power, and some of the sharpest minds on the planet. Take NASA, a breakthrough propulsion physics program, quietly resurrected under new names and budgets over the past decade. Their work reads like a wish list for rewriting the cosmos: quantum vacuum plasma thrusters that tap into zero-point energy, experiments with metamaterials designed to mimic the gravitational properties of negative mass, even attempts to measure microscopic spacetime distortions in lab-scale warp field experiments. One particularly audacious project involves using high-energy lasers to stimulate the quantum vacuum, essentially poking empty space until it coughs up usable energy. It's the kind of research that would have been dismissed as fantasy a generation ago, but today carries the weight of peer-reviewed papers and government grants. DARPA, never one to shy away from the impossible, took a different angle with its 100-year Starship initiative, a challenge to develop propulsion systems that could reach another star within a century. While not exclusively focused on warp tech, the program's most intriguing offshoots flirt with relativistic effects and spacetime manipulation. Their nascent light-matter interactions project explores how ultra-intense laser pulses might alter the fabric of space itself, while collaborations with quantum computing labs probe whether entanglement could be weaponized for instantaneous communication across interstellar distances. The unspoken thread running through all of this: if you can't break the speed of light, maybe you can cheat it. What makes these efforts so fascinating isn't just their ambition, it's their methodology. Unlike the lone genius tinkering in a garage, modern propulsion research operates at the intersection of supercomputer simulations, quantum labs, and orbital experiments. Machine learning algorithms scour decades of physics data for overlooked correlations, while microfabrication techniques create metamaterials with optical properties that defy nature. The tools themselves are revolutionary. Atomic interferometers can now measure spacetime distortions smaller than a proton's width, and quantum sensors detect gravitational anomalies that would have been invisible to Einstein. Yet for all the high-tech wizardry, the biggest obstacle remains philosophical. Traditional peer review often struggles to evaluate ideas that straddle the line between established physics and speculation. Proposals for warp field experiments or negative energy extraction frequently face skepticism, not because they violate known laws, but because they challenge the unspoken boundaries of respectable science. That's why programs like DARPA Defense Sciences Office are crucial. They provide a sandbox where radical concepts can be stress-tested without immediate pressure to deliver marketable results. The real payoff might not be a functioning warp drive at all, but the unintended discoveries along the way. Research into space-time manipulation has already spun off advances in quantum communication, ultra-precise navigation systems, and even new approaches to energy storage. It's a reminder that the path to rewriting physics isn't a straight line, it's a labyrinth where every dead end might hide a side door to something extraordinary. So while headlines fixate on whether we'll ever see a working Alcubierre drive, the quieter truth is that the pursuit itself is reshaping our understanding of the possible. Whether these programs ultimately crack warp technology or simply nudge us closer to the next paradigm shift, they've already achieved something remarkable, making the impossible feel inevitable. While government agencies tinker with the edges of possibility, private organizations are sprinting ahead, treating warp physics not as a distant dream, but as an engineering puzzle waiting to be cracked. At the forefront stands the Limitless Space Institute, a research hub founded by former NASA scientists with one audacious goal: to make interstellar travel achievable within our lifetime. Unlike traditional labs shackled by bureaucracy, LSI operates like a Silicon Valley moonshot, blending theoretical rigor with the disruptive energy of a startup. Their roadmap reads like a thriller: pinpoint feasible milestones from nanoscale spacetime distortions to prototype drives, then reverse engineer the steps to get there. What sets LSI apart is their embrace of incremental progress. Where most warp research fixates on the show-stopping Alcubierre metric, their team dissects smaller, testable phenomena that could inch us toward the ultimate breakthrough. Take their work on warp field interferometry light, a tabletop experiment designed to detect spacetime distortions 1 billion times weaker than those needed for actual propulsion. It's the equivalent of practicing scales before composing a symphony, but in this case, the instrument is the fabric of reality itself. Early results hint at anomalous energy signatures that defy classical explanations, though skeptics argue these could stem from experimental noise. For LSI, even inconclusive data is fuel. Each anomaly narrows the gap between theory and tangible effect. Funding this radical research requires equally unconventional thinking. Instead of relying solely on grants, LSI has built a coalition of billionaire backers, university partners, and even crowd-funded citizen science initiatives. Their pitch, warp capability, isn't just about exploration, it's the ultimate economic disruptor. Imagine a future where asteroid mining conglomerates bid for warp-equipped prospecting drones, or where pharmaceutical companies exploit time dilation to accelerate drug testing. By framing Starflight as an investable frontier, LSI has turned physics into a venture capital darling. Yet the Institute's most compelling asset might be its willingness to court controversy. While mainstream physics dismisses warp drives as century-scale projects, LSI's timelines border on provocative. Their Bacon program, named not for the philosopher but the aphorism, "Progress is made by trial and error," aims for a lab-scale warp demonstration within 15 years. Critics call this delusional. Supporters point to history's pattern of underestimating exponential progress. After all, the Wright brothers went from bicycle mechanics to powered flight in 4 years, while the atomic bomb leapt from scribbled equations to world-altering reality in 6. Parallel efforts are sprouting worldwide. Startups like Applied Physics leverage AI to simulate warp geometries impossible to calculate by hand, while university spin-offs explore metamaterials that mimic negative energy's properties. Even aerospace giants have war rooms gaming out scenarios. Boeing's secretive Horizon X division reportedly holds patents for spacetime propulsion concepts, so speculative they're classified as post-physics. The through line, a growing consensus that warp research, once the domain of fringe theorists, is entering its Edisonian phase, where systematic tinkering might stumble onto the filament that lights the way. What unites these ventures isn't just ambition, but a shared recognition of warp technology's cascading implications. Success wouldn't merely give us starships, it would redefine energy markets, reshape geopolitics, and potentially unlock entirely new branches of physics. The private sector's role isn't to replace cautious academia, but to inject urgency into the quest, proving that sometimes the best way to move mountains is to convince entrepreneurs there's gold buried inside. Predicting when humanity might crack warp technology feels less like forecasting and more like staring into a quantum haze where every potential outcome exists simultaneously until reality collapses into one. Optimists, often nestled in Silicon Valley labs or private aerospace startups, point to exponential trends in quantum computing, metamaterials, and energy manipulation. They argue that if progress continues at its current blistering pace, we could see proof-of-concept warp effects within 50 years, perhaps a microscopic spacetime distortion measurable in some underground supercollider or nanofabrication facility. These voices cite historical examples like the shockingly rapid development of nuclear power, from Einstein's scribbled mass energy equivalents to mushroom clouds over New Mexico in just 40 years. If funding and talent align, they suggest, warp could follow a similar trajectory from equation to engine. Realists counter with cold, hard physics. Even if we confirm the Alcubierre metric's viability tomorrow, scaling it to functional technology might require centuries of incremental breakthroughs. The leap from detecting a single distorted atom to moving a starship is comparable to progressing from a Neolithic wheel to a hypersonic jet, each intermediate step demanding entirely new disciplines. Energy production alone presents a generational hurdle. Current nuclear fusion reactors still can't break even, let alone generate Jupiter-scale exotic matter outputs. Conservative estimates place practical warp drives no sooner than the year 2500, assuming no civilization collapsing setbacks along the way. Pessimists, often astrophysicists steeped in cosmic timescales, offer an even starker view. They argue that warp travel might forever hover just beyond our reach, like a desert mirage that vanishes as we approach. The universe's fundamental constants, the speed of light, Planck's limits, entropy's arrow, could be immutable guardrails preventing faster-than-light travel for any intelligent species. In this scenario, humanity's interstellar future might resemble Polynesian navigation. Slow, patient voyages between islands of habitability using generation ships or hibernation tech, with warp remaining as fantastical as alchemy. Yet hidden between these projections are wildcards that could accelerate or derail progress. An accidental discovery in some high-energy physics lab, a new state of matter, an unforeseen quantum phenomenon might shortcut decades of research. Conversely, global instability or resource depletion could stall scientific advancement for generations. The rise of artificial superintelligence introduces another variable. A post-human mind might solve warp's equations in seconds or deem them irrelevant after uncovering deeper cosmic truths. Perhaps the most honest timeline acknowledges that warp technology isn't a singular invention but a spectrum of milestones. detectable warp effects could emerge within our lifetime, followed centuries later by unmanned probes, then crewed ships. The journey between impossible and routine might span longer than recorded human history, or collapse overnight if we stumble upon the universe's hidden keys. Until then, every experiment probing spacetime's flexibility, no matter how small, is a vote cast for a future where the stars aren't just points of light but destinations. Unlocking warp technology wouldn't just challenge our understanding of physics, it would force humanity to confront ethical dilemmas with existential stakes. Picture a world where any group with a warp drive could redirect asteroids toward cities or leapfrog nuclear deterrence by delivering payloads faster than warning systems can react. The same breakthrough that promises interstellar exploration also lowers the barrier to devastation, compressing the timeline between conflict and annihilation from minutes to milliseconds. This isn't merely theoretical. Physicists have calculated that a grapefruit-sized object warping into Earth at 90% light speed would strike with the energy of 200 Hiroshima bombs. Suddenly, the question shifts from can we to should we, yet the risks extend far beyond warfare. Warp capability could destabilize civilizations by creating irreversible knowledge gaps between those who control the technology and those left behind. Imagine corporations exploiting time dilation to outrace patent laws, developing centuries of research while competitors experience mere months. Or authoritarian regimes using warp bubbles as perfect prisons where dissidents age decades in isolation while the outside world moves forward without them. Even peaceful applications carry thorny implications. Terraforming projects might accidentally extinguish alien microbial life before we recognize its existence, or warp highways could slice through regions of space-time we don't yet understand, like cosmic bulldozers plowing through invisible ecosystems. The moral calculus grows murkier when considering unintended consequences. Some models suggest frequent warp travel might fray the fabric of space-time itself, creating dead zones where physics behaves unpredictably. What responsibility do we bear if our grandchildren inherit a galaxy scarred by irreversible distortions? Comparisons to climate change feel uncomfortably apt. Another case of short-term ambitions colliding with long-term sustainability, except warp's consequences could span light years rather than centuries. Even if the technology proves safe, its mere existence might trigger existential panic historically. Civilizations encountering sudden technological leaps often fracture under the strain. Would revealing warp capability spark a new dark age as societies recoil from its implications? Counterarguments highlight humanity's resilience. Every major technological leap, fire, electricity, nuclear power, was initially weaponized before being harnessed for progress. Proponents argue that withholding warp research out of fear would be its own ethical failure, condemning our species to a single planetary fate when cosmic expansion offers survival insurance against asteroids, supervolcanoes, or future solar instability. They point to the Outer Space Treaty as precedent proof that nations can cooperatively regulate transformative technologies when survival depends on it. Perhaps the most profound dilemma lies in whether we can ethically withhold warp technology if alien civilizations already possess it. The Fermi paradox suggests advanced societies might avoid contact to prevent cultural disruption, a galactic prime directive enforced through self-restraint. If we detect warp signatures from neighboring stars, do we mirror their caution or risk becoming the reckless newcomers who shatter cosmic norms? These questions demand more than scientific consensus. They require philosophical frameworks we haven't yet invented. The atoms we're made of were forged in dying stars. Do we owe the universe equal care when bending its structure to our will? Unlike climate change or nuclear proliferation, warp ethics can't rely on historical precedent. We're drafting moral codes for scenarios no species may have faced before, where actions ripple across millennia and light years simultaneously. The ultimate test won't be whether we can build a warp drive, but whether we can grow wise enough to wield it without becoming architects of our own obsolescence. The moment warp technology transitions from equations to reality, humanity's view of our place in the cosmos would undergo a seismic shift, not just scientifically but philosophically. For millennia, the vast distances between stars served as a buffer against existential dread, a quiet reassurance that whatever lurked beyond our solar system couldn't easily reach us. Warp capability would shatter that illusion, transforming the universe from an insurmountable expanse into a navigable neighborhood. Overnight, the great silence of the Fermi paradox, the eerie absence of detectable alien civilizations, would take on urgent new dimensions. If the stars are suddenly within reach, why haven't others visited us already? The answers could either comfort or terrify. Perhaps advanced societies self-destruct upon discovering warp physics, or worse, avoid contact because they know something we don't about the dangers of bending space-time. Religious traditions would face their own reckonings. Sacred texts describing heavens beyond the clouds never accounted for beings who could cross light years in hours, raising profound questions about divinity's scale. Would souls traversing warp bubbles still journey to an afterlife? Or might death itself become negotiable if time dilation allows near immortality? Some faiths might reinterpret warp drives as fulfillment of ancient prophecies, modern chariots of fire carrying believers to celestial realms. Others could fracture over whether manipulating space-time violates divine natural law, echoing historical schisms caused by heliocentrism or evolution. The very concept of creation might expand to encompass civilizations who have learned to tweak the universe's underlying code, blurring the line between worshipping gods and becoming them. Art and culture would ripple with newfound themes. The archetype of the lone explorer, from Odysseus to Interstellar protagonists, would give way to narratives about communal starflight, entire societies unmoored from linear time, or generations living aboard warp-capable arcs. Music might incorporate the eerie harmonics of quantum vacuum fluctuations, while visual artists could experiment with portraying higher dimensional distortions. Even language would adapt. Words like distance and journey might shed their terrestrial meanings, just as friend transformed when social media detached it from physical proximity. On a societal level, warp capability could either unite or fracture humanity. Shared awe at the technology might dissolve borders, forging a planetary identity focused on interstellar stewardship. Alternatively, disparities in access could ignite new colonialisms, warp-capable elites exploiting Earth-bound majorities, or corporations claiming exoplanets through sheer mobility advantage. The psychological toll alone would be staggering. How does one maintain mental health when entire civilizations rise and fall within a single warp traveler's lifetime? Yet the most profound change might be metacognitive, the realization that space-time, once considered the immutable stage of existence, is merely another frontier to be explored and reshaped. That shift in perspective could eclipse even the Copernican revolution, teaching us humility not through our smallness, but through our newfound responsibility as caretakers of reality's fabric. The stars may have birthed the atoms in our bodies, but with warp drives we'd become more than stardust. We'd become shapers of the cosmic order itself. The flickering lights zigzagging across the night sky, sudden acceleration, impossible turns, vanishing without a trace, have fueled UFO speculation for decades. But what if these aren't just unexplained phenomena? What if they're glimpses of advanced propulsion systems bending the very fabric of space? The idea that some UFO sightings could represent extraterrestrial warp technology isn't just sci-fi fantasy. It's a hypothesis that forces us to confront startling possibilities about both alien civilizations and the limits of our own physics. Consider the U.S. Navy's now declassified encounters with objects exhibiting movement patterns that defy conventional aerodynamics: instantaneous acceleration, hypersonic speeds without sonic booms, abrupt 90-degree turns at velocities that would pulverize any known aircraft. These aren't just quirks of misidentification, they align eerily with theoretical warp drive behavior. An Alcubierre bubble, for instance, would compress space ahead of a craft, allowing it to move without accelerating through the intervening air. No G-forces, no shockwaves. Observers might see a luminous distortion as the warp field interacts with atmospheric particles, creating the trademark glowing halos reported in countless UFO cases. Even the sudden disappearances fit. A collapsing warp bubble could redshift light to invisibility as the craft transitions out of local spacetime. The implications are profound. If even a fraction of UFO sightings stem from warp-capable vehicles, it suggests civilizations mastering physics were still scribbling equations about. Their technology wouldn't just be ahead of ours, it would redefine what advanced means. Imagine a society that treats spacetime like a highway system, weaving between stars as casually as we commute between cities. Their very presence, if intentional, could range from scientific curiosity to a form of interstellar zoning compliance, studying emergent species like we monitor protected wildlife, ensuring we don't stumble onto galactic freeways before understanding the rules. Yet the hypothesis isn't without flaws. The energy signatures of a functioning warp drive should theoretically be enormous gamma-ray bursts, gravitational lensing, or Cherenkov-like radiation from particles trapped in the bubble's wake. Most UFO sightings lack these telltale markers, leaving skeptics to argue they're more likely classified military projects or atmospheric oddities. Even if some cases defy conventional explanation, conflating them with warp tech risks mirroring ancient cultures mistaking eclipses for divine wrath, a premature leap to cosmic conclusions when simpler answers may lurk in undiscovered terrestrial physics. Perhaps the most tantalizing clue lies in consistency. Across decades and continents, a subset of UFO reports describe crafts exhibiting the same impossible maneuvers, a pattern that could suggest common underlying technology. If these aren't random hoaxes or hallucinations but fractured glimpses of a single phenomenon, the statistical improbability grows harder to dismiss. Advanced civilizations might share universal solutions to space travel, converging on warp-like propulsion just as earthly cultures independently invented wheels or bows. The truth remains veiled, but the speculation serves a purpose beyond chasing lights in the sky. It pressures our scientific frameworks to stretch, testing whether our models of reality can accommodate not just hypothetical warp drives, but the tangible evidence, or lack thereof, that flickers at the edges of perception. Until definitive proof emerges, UFOs will linger in the liminal space between myth and physics, challenging us to ask not just, are we alone? But what feats might the universe allow when intelligence has a billion-year head start? Picture an Earth no longer bound by the limits of our solar system, a future where cities glow under the light of alien suns, where children learn about Mars not as a distant frontier but as the neighbor next door. With warp capability, humanity's expansion across the stars wouldn't just be possible, it would be inevitable. The first colonies might start modestly, domed enclaves on Proxima Centauri b, their translucent roofs filtering the crimson light of a dwarf star, while subterranean farms tap geothermal vents to grow crops in soils never touched by earthly seasons. These outposts would grow into sprawling arcologies, their architectures adapted to alien gravities, spiral towers on high G-worlds, floating habitats in thin atmospheres. And as generations pass, these settlements would diverge, shaped by their new homes until humanity becomes a tapestry of cultures as varied as the stars they orbit. But colonization is just the beginning. Warp technology would redefine first contact, turning the hypothetical into the imminent. Imagine a reconnaissance probe stumbling upon an alien megastructure, a Dyson swarm humming with activity, its builders unaware of our presence until a warp-capable scout breaches their perimeter. Would they greet us as peers or pests? The dynamics shift if we're the advanced ones. Warp-driven survey ships discovering pre-industrial civilizations on lush exoplanets, forcing us to confront our own prime directive. Do we observe silently, make contact, or in the darkest timeline exploit? The ethics would dwarf any terrestrial dilemma, compounded by the sheer speed at which conflict could escalate when worlds are hours apart instead of light years. Cosmic engineering projects, once the realm of supercomputers and whiteboard dreams, would become feasible. Warp-enabled construction fleets could dismantle gas giants for fuel, encase stars in energy-harvesting grids, or even attempt stellar husbandry, nudging red dwarfs closer together to create warmer hubs for habitation. The most ambitious visions flirt with rewriting galactic geography, using warp fields to tow rogue planets into stable orbits, or threading wormholes between star systems to create a subway network for civilizations. These wouldn't just be engineering feats, they'd be acts of creation, placing humanity in the role of celestial architects, yet every golden age casts shadows. The same technology that lets us rescue species from dying worlds could also unleash predatory corporations strip mining pristine exoplanets. Political factions might splinter across interstellar distances, their disputes erupting into wars where weapons distort space-time itself. And lurking beneath it all, the haunting possibility that we're not the first to reach this stage. Ancient ruins on frozen moons or cryptic signals from galactic voids could hint at civilizations that ascended too fast, their warp signatures fading like echoes in the dark. The most profound change might be existential. With the stars suddenly within reach, humanity's narrative would shift from a single planet species to a cosmic diaspora. Art would grapple with alien landscapes, religions would incorporate celestial journeys into their cosmologies, and history books would partition epochs into before warp and after. The night sky, once a static tapestry, would become a living map, every flickering dot a potential home, a threat or a mystery waiting to be unwarped. The ultimate question isn't whether we'll reach this future, but whether we'll recognize ourselves when we get there. After centuries of gazing at the stars with longing, we stand at a crossroads between science fiction and scientific possibility. The dream of warp drive isn't just about velocity, it's about rewriting humanity's role in the cosmos. What have we learned? That space-time is more malleable than we once thought, that equations penned decades ago still hold tantalizing loopholes, and that every impossible barrier is just a puzzle waiting for the right perspective. The Alcubierre metric showed us how to fold space instead of fighting it. Quantum fluctuations teased the existence of negative energy, and while the energy requirements remain astronomical, history whispers a crucial lesson. Today's deal-breakers often become tomorrow's engineering challenges. Yet for all the progress, warp technology remains a tightrope walk across uncharted physics. We've mapped the theoretical roadblocks, causality violations, lethal radiation, exotic matter shortages, but we've also watched once insurmountable walls crumble before. Remember when breaking the sound barrier was called a physiological impossibility, or when skeptics insisted heavier than air flight defied the laws of nature? The pattern is clear. Impossibility is often just a lack of imagination wearing the mask of authority. This isn't blind optimism. It's the recognition that every revolutionary technology was once dismissed until someone proved otherwise. The real value of warp research isn't just in chasing starflight, it's in the collateral discoveries lighting our path. Quantum vacuum experiments have already revolutionized precision measurement. Warp field math has deepened our grasp of general relativity. Even failed prototypes push material science and energy systems forward. These aren't consolation prizes, they're stepping stones toward mastery over space-time itself. Consider how NASA Apollo programs spun off everything from MRI machines to fireproof fabrics, proof that aiming for the stars reshapes life on Earth in ways we can't predict. So where does this leave us? Not with a blueprint for a starship, but with something more vital, a mandate to keep probing the unknown. The greatest risk isn't hitting dead ends, it's abandoning the search too soon. Whether warp drives become reality in 50 years or 500, each experiment inches us closer to understanding the universe's deepest rhythms. And if we persevere, future generations may look back on this era not as the time we failed to build a warp engine, but as the moment we began thinking like a civilization destined for the stars. The night sky's silence isn't an indictment of our limits, it's an invitation. An invitation to test, to fail, to refine, and to one day step into the cosmic currents with the confidence of travelers who have earned their place among the constellations. Until then, we keep asking, keep calculating, and keep our eyes on the horizon where science and wonder meet. The stars aren't just points of light anymore, they're reminders that every impossible journey begins with a question no one's brave enough to answer until someone does.